let's do a flash review. We start with a column. The slower things are interacting more with the stationary phase, while the faster things don't spend as much time with the stationary phase. As these are separated and they go down the column, you can either stop the separation early when you still have narrow peaks that are tall, or you can wait until you get well-separated peaks, and this is a trade-off that we're going to have to deal with in all parts of chromatography that we look at. Next, we learned about the distribution constant, which is a capital K. This is a way that we can describe the equilibrium between the target analyte on the mobile phase and the target analyte in the stationary phase. This is defined in terms of the activity of the analytes, but at low concentrations, we can calculate this as being the ratio of the concentrations instead of the activities. This is awesome. It lets us have linear chromatography where we get Gaussian peaks. However, real life isn't ideal. So most of the time we'll not have Gaussian peaks to deal with, but it makes the math easier for the rest of our section to live in this world. Next, we looked at the retention time and saw that we can calculate this being the amount of time that the target analyte spends on the stationary phase plus the amount of time that it spends on the mobile phase. We saw that we could find the time that it spends in the mobile phase on a chromatogram and the retention time from a chromatogram, and then obviously we would be able to calculate the time that the analyte spends in the stationary phase. We also learned that we can use the retention time and the column length to calculate the rate and the mobile phase linear velocity from that time that it spends in the mobile phase. These are both linear velocities, not volumetric velocities, and you may be more used to hearing about milliliters per minute than centimeters per second. So just be aware of that. After retention time, we looked at retention factor, which is very similar to the distribution constant, except for that it is a lowercase k and it accounts for the volumes of the stationary phase and the mobile phase. And we can calculate this easily from the chromatogram by the retention time and the time of migration for the mobile phase. We can also look at the selectivity factor. This is always between an analyte A and B, where A is eluting first and B is eluting last because the selectivity factor has to be greater than 1. Finally, we learned about resolution, which is simply a measurement of how narrow the peaks are versus how well separated they are. And so we divide the difference in retention times by the average width of the peaks at the base. Although, as we learned, we could also use the full width at half max, but then we have to change our resolution equation, and there are other equations for that. So, when we step back, these are all the things that we learned in the last lecture. I'll stop here, and the next video will pick back up where we left off, and we'll start to learn about rate theory.